Alright, I just wanted to make a short video to cover some of the things I missed in 4.1 in class time. And so these are from Nicholson, which has some really nice results. First of all, theorem 4.1. If R is a ring, X is indeterminate over R. We prove that R adjoint X is a ring, that we can identify R as the subring of constant polynomials. 3. If Z is the center, then the center of the ring of polynomials is just the polynomials with coefficients from the center. X commutes with everything. And finally, if R is commutative, then polynomials over R are also commutative. So basically 1, 2, this is a very low-tech presentation, guys. So 1 and 2 follow from our construction in last class. If 3 holds, that means that if 1 is in the center, right? So x is 1 times x, which means that x is in the center of the polynomials. In other words, 3 implies 4. Let me zoom back out a little bit here. So 3 implies 4. And likewise, if 3 holds, you can also get 5, because if the center of the ring is the whole ring, in other words, if the ring is commutative, then that implies that the center of the polynomials is the polynomials over the center, which in this case is the whole ring, so that shows that every polynomial commutes with every other polynomial. So basically, if we can show 3, we automatically get 4 and 5. So to prove 3, we just look at f and g polynomials where f is coefficients from the center, and if you multiply f times g using the term, using the multiplication that we defined in terms of sequences and such last class. Sorry, I gotta scroll down. I'm not a very good cameraman. Using the multiplication we defined last time, and just collecting, usual polynomial multiplication, which we constructed last class. The fact that these commute with every coefficient in f commutes with all of the coefficients in g allows us to turn them around. And so we get f times g is g times f, which is to say that f is in the center. And then conversely, if you have a polynomial with which is in the center, well, it commutes with everything in the ring of polynomials, which means in particular it commutes with constant polynomials, which then gives you that the coefficients of f must be in the center of the ring because they commute with everything in the ring, which is to say that f is built with coefficients from the center. So that's 3. So that's theorem 1 in section 4.1. I think is worth, of course, you guys, if you just read the section, then I'm not really doing much for you here, but I'm afraid, well, anyway, I just think it's wise for us to post this video. It won't take much of your time. And basically, I'm just reading through section 4.1 with you, with a few extra comments here and there. Lemma 3 says that the ideal generated by x, all right, polynomial multiples of x, well, that's an ideal, and r of x mod the ideal generated by x is isomorphic to R. The proof is basically by this evaluation, this theta map, which, if you look at it, it's nothing more than plugging 0 into x. You can think of it that way. This is actually the evaluation at 0 map. So later in the section, he's got a proof that the evaluation homomorphism is a homomorphism, so, there you go. But he does have a standalone proof that theta is a ring homomorphism here. Great. More interestingly, it's onto, because the constant polynomial maps to R, and R is anything in the ring, so that gives us onto. And the kernel, in other words, the polynomials which map to 0 under theta, that just puts the constant term 0, but if the constant term is 0, you can factor an x out of everything that remains, which gives you x times this, but that's an arbitrary polynomial, which means that this is nothing more than the ideal generated by x. And finally, first isomorphism theorem gives me that polynomials mod this ideal is isomorphic to the image, which is the whole thing since it's onto. So that's lemma 3, which is neat. Theorem 2 is a little bit more interesting. And so let R be a domain. That means that it has no zero divisors, but it doesn't imply that it doesn't have to be commutative, right? An integral domain is a commutative domain in our language. Then polynomials built polynomials with coefficients from the domain form a domain. If we have f and g non-zero in the polynomials of our domain, then the degree of the product is the sum of the degrees. And also the units in the domain are precisely the units of R. In other words, the only polynomials which multiply to give you 1 are constant polynomials, and only then if those constants are not non-zero divisors and such. So the proof is pretty straightforward, but worth looking at. So we know that this is a ring with unity. It remains to show that it has no zero divisors. So let f and g both be non-zero polynomials with leading coefficients non-zero. Here's their explicit expressions. Then by construction, the degree of f is m, the degree of g is n. And then we multiply. All right. So the multiplication is just the rule we wrote out last time, we constructed last time. It's the usual multiplication. To get the constants, you multiply the constants, right? Linear terms come from constant times the first, and the first times the constant. Be careful not to commute them, because R is not commutative, so we have to write a naught b1 plus a1 b naught, and so forth. But the largest thing here is am b to the m, am bn, x to the m plus n. So that says if fg is equal to 0, that implies that every coefficient here is 0. In particular, am bn is 0. But if am and bn are not equal to 0, that is a contradiction, because in a domain you can't have the product of two non-zero things be 0. Consequently, f times g is not 0, and that implies that R of x is a domain. Also, from the same calculation, loosen the restrict. Suppose R is not a domain, right? If R is not a domain, then it could be that this is 0, right? But from this equation, you can also see that the degree of f times g is is at most the degree of f plus the degree of g. That's also implicit here, which is something I come back to here in a minute. But anyway, it's clear from in the context that R is a domain, the degree of the product is m plus n, which is the degree of f plus the degree of g. Finally, part 3. I tried a direct proof, and I kind of went, oh, this is actually kind of hard. And then I thought, well, you know what I should do is I should use the degree. Notice that the degree of f times g, well, if fg is equal to 1, right? That's what we want to think about. If f is a unit, then there exists a g such that fg is equal to 1, right? So if I have fg equals to 1, I also have the degree of fg is equal to the degree of f plus degree of g, but the degree of 1 is 0. And these are non-negative, which forces both of these to be 0, which is to say that both f and g are constant polynomials. Consequently, the units of the polynomial ring are just the units of the ring. And I mentioned that this proof also gives theorem 3, which is on my next page. Let's see here. So this is theorem 3, which is that if we have the two non-zero polynomials in the ring, and either f or g has a unit as a leading coefficient, then their product is non-zero, and the degree formula is natural. Of course, if R is not a domain, then we have this lemma, also from the previous proof that I just went through. Again, for f and g polynomials in a general ring, then we just get that the degree of f times g is less than or equal to the degree of f times the degree of g. This is illustrated by example 5, which I'll get to in just a second here. Again, that was the star equation from the last page. The point here is that that doesn't have to be non-zero for R not a domain. Okay, I think I've said that enough. Example 5 is really neat. Here we have 1 plus 2x with coefficients from z4. Of course, this is not a domain because z4 has 0 divisors. And f squared ends up being equal to 1, which means f is its own inverse. F is a unit in z4x, right? And yet f is certainly not constant. So when we're outside the context of a domain, we can have units which are not constants, which is kind of neat. But that's not automatic. His next comment Nicholson makes is that it's not automatic. You can have units it could be that the only units for something not a domain are still just in the underlying ring. I think that's the point of his next example. If you have f as a field, you look at the direct product of the polynomials and polynomials, that's isomorphic to the direct product of f with x. And well, sorry, I'm tempted to write down the isomorphism, but I'll shut up. It's not really the point here. You could find an isomorphism. Maybe that'd be a good test question, actually, but anyway. So the ring here is the field across the field. Of course, if you take like 1, 0 or 0, 1, these are zero divisors because they're non-zeros. So you multiply 1, 0 with 0, 1, you get 0, 0, but neither of them are 0. It's got zero divisors. And I mean, any product ring has zero divisors, right? And anyway, that he claims that you can show that the units for these polynomials just contain constant polynomials. All right, so what happened in example 5 doesn't always have to happen, is his point there. Enough about that. Here's the division algorithm, which I stated last time, and I'll really sketch some of the proof here. The proof is actually kind of neat. It's worth a minute. So R is a ring, f and g polynomials, f non-zero, with a leading coefficient of a unit. Suppose the degree of f of n, if f is n, and again u is a unit. Then there exist unique polynomials q and r, such that g is equal to qf plus r, and either r is 0 or the degree of r is strictly less than f. So I'll follow Nicholson's proof. So he says m is the degree of g, n is the degree of f. He starts out by pointing out that if g is 0 or m is less than n, then if we just look at g is equal to 0 times f plus g, that suffices to establish the result. All right. So what we'll do is we'll suppose that m is greater than or equal to n and use induction on m. So let's just write it out. We have f looks like this, and he's clever to reduce the clutter here. He just writes the leading terms and leaves this to your imagination. But of course it goes down to constants, right? And here's the leading term in g plus constant stuff. And this is the standard argument, I suppose. g1, you construct a new polynomial by, although you know this is not entirely standard. From other books might not deal with this quite as generally. You notice that r is not assumed to be commutative here, which is kind of cool. And yet this argument works. So g1 is g minus b u inverse, which exists because u is an inverse, use a unit rather, x to the m minus n times f. So you write this out, g is that, and then b is this, expanding f as what it is, but then you multiply stuff out. I mean, that's just these again. And then down here, x to the m minus n commutes with u, because x and any power of x commutes with anything in the ring by construction of the polynomials. So u x to the m minus n is u times x to the m minus n, and then over here again I can push the a past that when I multiply, and then cleaning things up a bit, we get bx to the m and minus bx to the m, which is the whole point of subtracting this thing, is it cancels out the leading term in g, and so we're left with a polynomial that has order at most m minus 1. Now of course if g is equal to 0, then we're done. So otherwise the degree of g is less than m at least. All right, if it's non-zero, then we can use induction, because we're proceeding by induction on m, to find polynomials q1 and r such that g1 constructs q1 f plus r is equal to g1, where again r is either 0 or the degree of r is less than the degree of f. But then if you just plug that back up into here, solve for g is equal to g1 plus this stuff, right? And so let me pan down here a bit. Oh, I'm sorry. Let me go back to that again. So either g1 0 or the degree of g is less, degree of g1 is less than m. So by induction we get q1 and r such that g1 is q1f plus r. All right. Either r is 0 or the degree of r is less than the degree of f. So you just take that and plug this back up into the g up here. I missed my lightsabers. Oh well. and then we get g is equal to g1 plus that, but if you put back what g1 is, you can collect the f terms together and get this stuff times f plus r, which is a polynomial times f plus r, where r meets the needed conditions, so that completes the induction step. All right, and then I'll let you look at Nicholson for uniqueness, because, well, I want to go on here. What I think is more interesting, and most of the reason I'm making this video actually, is what I'm showing you right now. Why commutative rings are so nice, and just the danger of evaluation. If we have, in the non-commutative context, if we have polynomial, and we have a in the ring, substituting a is subtle in non-commutative context. For example, f equals to x minus a times x plus b. All right, if we plug in the a into this expression, we get a minus a plus b, which is 0. But on the other hand, if we take this and multiply it out first to get x squared plus b minus a x minus ab, and then we plug in a, we get this a squared plus ba minus a squared minus ab, so the a squareds cancel. But oh no, we're left with ba minus ab, which doesn't have to be 0 in a non-commutative context. This is very troubling. It means that if we evaluate before or after we do algebra, we get different answers. That it's not cool, right? So you know, again, I'm sorry, I keep talking off the screen. F of a is this. So you see, what, after we multiply out, maybe I should just zoom out a little bit. Sorry, guys. After we zoom out a bit, if we multiply that and plug in a, we get not 0. We can't have 0 and not 0. The reason that this failed for us is because the fact that x commutes with r is built into our construction of polynomials. But if we substitute in x naught, which is not in the center, then of course x naught r is not equal to r x naught for some r, and so it's possible we're going to get into trouble with the evaluation. In fact, the next theorem, which I have folded away my, well, here, a second, let me fix that. Oh, fine. There. So this is the evaluation theorem, and it says exactly what you'd think. If we have our ring and a is in the center of the ring, it's important that it's in the center, then we can define the evaluation map, where we just replace x with a to the appropriate power. Then this is a surjective ring homomorphism. The fact that it's surjective is easy. It's also pretty clear that it's well defined. Additivity isn't hard to do either. But let me just sketch the basic argument here is you need it to be in the center to avoid what I showed you on the last page. When you look at multiplicativity, basically we need to be able to commute the a past the coefficients of the polynomial, and in order to do that, I need that a is in the center. If you don't have that, then you get into the trouble we looked at in the last time. So it's important for a non-commutative ring, if you're going to use the evaluation map, you can only use it at things in the center. Now, we're almost always in the commutative ring context past this point in Nicholson, so it's not really an issue because a is always in the center, because the center is the whole thing. But anyway, I thought this was an interesting, I really enjoy this theorem and the discussion leading up to it. I think it's very pretty. What remains in section 4.1 is in my notes, which are posted that I went over last time, so I'll just leave it at that, guys. Thanks.